Hi class, these are additional notes. I realized in lecture I kind of blew past certain things and maybe I didn't go over it in explicit detail, and so this is basically a video to supplement what I was talking about in class to make some things a little clearer. Now, when you look at all these different games that we've talked about in this lecture, what it comes down to is they kind of follow a pattern. And your first two steps are either to make a decision tree or a payoff table. Now, eventually you will make a payoff table because you're going to want to see what the optimal spaces are, basically your equilibrium points. The decision trees are helpful because they help you form the payoff table, which some people actually can do the table first right away. It's easier for them because they think in terms of tables. Some people, they need to have the tree first in order to figure out where they're going to put all their variables. So is there a right way or wrong way to do it? Nah. I tend to start with tables, but if it's really complex, then I like to do trees so I can see the whole thing. Now, based on what those payoffs are, you can actually derive the probabilities of where you tip one way or the other. For example, if going right has a much higher probability than going left, then naturally that changes your payoffs because you have different expectations. And so based on that, you can come up with a function or a discrete rule that tells you where you should be operating. And those are your equilibrium points. Where's your best strategy? And that's what you get from those calculations. So that's the base process. When I talked about duopoly, a big part of it is your reaction curve. And your reaction curve is basically when do you get optimal performance, when marginal revenue equals marginal cost. And so figuring out what my quantity should be based on what the other guy's quantity should be, then that's where we should be operating. Now, the one thing that does happen though is that if you can cooperate, meaning you make less and I'll make more, and as it turns out maybe we'll make more profit as opposed to us making the same number. You don't know, but this is what they refer to as collusive outcomes, and you have to have an agreement between you that you're going to split the profits, and that's what this whole calculation is about. Giving you examples of that. Also, there's the issue of first mover, that if I go first, then where does that put me? Where should I be operating? And so when we talk about mixed strategies, it means that no dominant strategy exists. So the question is, based on what that guy does, what should I do? And then does it make a difference if he goes first or second? Well, numerically, what do we always do? We always look at expectations. And so the expected value, we go with whatever's higher. And so in this case, here are the payoffs of a game that we talked about. Should I go forward or backward based on him going left and right? So we're like hunting each other. Well, in terms of player 2, he has a probability of going left, and then 1 minus that probability of going left is him going right. Same thing with forwards and backwards. And so what's my expected value? Well, my expected value is my payoff times the probability. And so in terms of player 1 backward, you add 4 PL plus 2 times 1 minus PL, and that gives you the expected value of him going backward. And you do exactly the same thing for him going forward. And you do the same calculation for the columns to get the expected value of left or right. So what I've shown is the calculation that if EB is greater than EF, then that means I'm going to go backwards. If EF is greater than EB, then I'm going to go forwards. And essentially the probability that I calculate in doing that calculation is what my equilibrium probability is, meaning it's equal. I have the same return left and right. Naturally, I want a dominant strategy. If it's exactly in the middle and they're exactly the same, then it doesn't matter what I pick. It's just white noise. But I would rather have a choice where I have a clear-cut way to win. And so as you can see, that's where we come up with the calculation. And the same thing actually goes for player 2. So it comes out to be a third, 2/3, quarter, and 3/4. Now based on that, we can figure out the probability of every event. So the probability of me going left and player 1 choosing to go backwards is those probabilities multiplied together. And if you add up all 4 probabilities in the boxes, they come out to 1. So it's just 1/3 times 3/4 gives me that there's a 1 in 4 chance that player 2 will go left and I'll go backwards. And so based on those, you can figure out what your expected payoff is by totaling up that based on this strategy going on, what's the expected payoff of player 1 and player 2. So player 2 has a much better chance of doing better in this game. And what's probably really hurting player 1 is that 0 if he goes left and forward. But guess what? That tells you that if I can change the probabilities by changing the terms of the game somehow, that's the point I want to get rid of. There are different games. In this case, it's the game of cooperation. And the game of cooperation is, what are the points where both of us want the same thing to happen? And so if one goes high and one goes low, then we both lose. And so that's where you see the 0-0s. Ideally, we both like to go high. And so examples of games of cooperation is war. You want your allies to want the same things that you do. Driving on the road, you don't want people running into each other. If you're part of a cartel or oligopoly, you want the same thing. And so there are Nash equilibria present. And what a reaction curve is, again, is where is my optimal response. And so my optimal response is that I want to do high P, which has a 25% chance, because I'd rather have the high Q. And I do that regardless of what the other party is doing. And then the points that we overlap, those are the points we should be working at. And so we gave the example of chicken. And that's, again, all the game of chicken really is based on how they respond versus we respond. What are the outcomes? And from those outcomes, we can figure out the optimal probabilities. Or is there, of course, if there's a dominant strategy right away, then that makes things a lot easier for us. And so the game of chicken is either do I go straight or do I get out of the way? And you could actually, based on the previous payoffs, I just use the words hold and swerve, but I could have just as easily as used given and hold. Same thing. And so where are the optimal responses where we should operate? Same thing with the game of the vegetable game that we went over. And there are times that you might need to use threats because you want to go one way or the other, and it could be against one's incentives. The lazy husband game we talked about cleaning and not cleaning, and you can go over these details, but as you can see, the playoffs are much different depending on who goes first and who goes second. So what are the types of things we can do to change the odds in a game if we don't like them? And these are the things, is that I want to if I can do things to increase their number of options and make their strategy space more complex, I'm going to do it. Because all decisions are eventually going to come down to time, and I could do it more quickly than they are. Create lower payoffs, like poison pill contracts. That's why they institute them. And that means that, for example, I'm going to license you my technology. And this actually really happened, and it happened with the gyroscope. The company we licensed technology to had 1 year to get it into pilot production. If they didn't, they'd have to pay my company $1 million. And why do they do that? Because companies especially potential competitors, want to take your technology off the market. So they say, oh, yeah, we'll commercialize it, and then they don't do anything. Meanwhile, you've lost a year, and they've taken put a competitor, a potential competitor, a year behind. And so you put poison pills in, like, okay, if you don't have this commercialized in a year, you're going to have to pay us $1 million. And if you don't do it in 2 years, then it goes up to $3 million. And so you make it hard on them. You make it hard. You have poison pills in your cell phone contracts. If you switch out, there are penalty fees. Or what actions can help you, and that's like, can you create other incentives? So these are the types of things you can do. So you can calculate a game, but then you can think about, okay, well, how can I change the game? And that's why this is a really useful exercise in mapping. Because once you see where the weak points are, the strong points are, then you can figure out, okay, this is the way I want to change the game. And so if you remember the pricing game that we played, that really illustrates it. Right away you think there's a way to win, and as it turns out, there isn't. And so when you look at all these 6 different games in this lecture, it could be applied to different things, whether it's alliances or bluffing or negotiation. And really, when you look at all these games, the calculations are the same. What it pretty much just comes down to is the difference is what are the payoffs, because the payoffs create different kinds of equilibria. Some games are sensitive to first mover, some games aren't sensitive to first mover. And so the things that we talked about have to do with the response duopoly. And should I collude? That's another factor that goes into who goes first and who goes second. So I hope that clears some things up. Yeah, even I get punchy having to lecture that late. But on the bright side, I'm always thinking about you.